Hello from the other side. We're going to continue our discussion with Adele and how we can use this to help us find our directional derivative. Now we're going to use this formula right here, and it should look very familiar. We talked about this in our first example in the notes from the last video. Take a look at it if you need to again. Where if I want to find the directional derivative, we multiplied our partials, the vector containing our partials, we multiplied that by the vector containing our directional derivative. So we have our partials dotted with our direction vector as a unit vector. And that's exactly what our formula down here tells us to do. To find the directional vector at a point, we're going to take our del, remember the del, that was our list of partials as a vector, and we're going to dot that with our unit direction vector. In other words, it's going to look like this. It's going to be del f time dotted with u. And this is how we find our directional vector. Right there. So that's going to be the formula we're going to use. So let's take a look at a very quick example. We want to find the change. Oh no, it says the word change. Anytime we talk about change in math, of course, we are looking at a derivative pretty much. So in our function, in the direction of 1, 1, at the point negative 2, 1. And this should look very familiar. It's the exact same problem we saw up here. So let's go ahead and do that. According to our rule, to find duff, we're going to need del f. Our rule, we need our list of our partials. We can do that in our head. That's not too bad. The partial with respect to x, there we go, is of course 2x y cubed. And the partial with respect to y becomes 3x squared y squared. I am going to find my directional vector, my del f. I'm sorry, not my directional vector, sorry. I'm going to find my del at the point, negative 2, 1. And if I plug that in, well, let's see, here we would get negative 4. Whoops, let me see this. We would get negative 4. Plug in negative 2 here, we would get 12. Now, you might recall, we have a special name for this. This is what's called the gradient. And the gradient gives us the direction of maximum increase. So basically what this says, if I'm on this function at this point going in this direction, negative 4 up 12, if I head in this direction, it's going to give me the slope, the maximum, the direction of maximum increase on that slope. All right, anyway, so that's what that is. We need our unit vector. Let me go back to black. Sorry. There we go. We got to find our unit vector, which is not too hard to do. We already did that before. 1 over root 2. 1 over root 2. Right? We get that from here. Right? This is v over the magnitude of v. And then I just dot them together. Duffman. We take our negative 4, 12. We dot that with this 1 over root 2. 1 over root 2. And of course, we're going to get the same answer, 8 over root 2. And that's just how we use del in order to get the direction of the del to get our directional derivative right here. And that's and remember, this is the slope. Remember, this is not the gradient. This isn't the gradient because this gives me the direction of maximum increase. The directional derivative is not the gradient. The directional gradient, this gives us the slope in a particular direction. In other words, where the gradient, and again, we're going to talk about the gradient more tomorrow, where the gradient gives us the direction of maximum increase, the directional derivative gives us the slope in a particular direction. Sorry. Alright, I hope you enjoyed the video. Please join us tomorrow when we start talking about the gradient. I'll see you then. Bye-bye.